All right, I want to do a video about related rates here. And for this video, what I want to do is remind you about implicit differentiation. Because once you know how to do implicit differentiation, then related rate problems are not that difficult, okay? So let's look at this particular example here. Now I want to point out what we're going to do is we're going to look at this in terms of time instead, okay? So instead of x. And so that just makes it a little bit different. So if we do our first step of implicit differentiation, and we take the d of both sides, that's got to be the same as what we've done before, right? That's that first step, take the d there. Okay, but then what we can do is we do this, the derivative of y is just going to be 1 times dy, and then the derivative of x squared would be 2x, and then a hidden chain rule, dx, okay? And then what we do here is that we're going to divide by time. We're going to divide by t, since it's with respect to time, okay? And so what we'll do is we'll divide each of these pieces here by t. And again, remind yourself that it's convenient to put the dt underneath the dx here, okay? The last step would be to solve for dy dt, but in this case, we're done, okay? So that's the basic idea, and you'll see it'll be a little bit different. Now, we'll do time. It's pretty a common one for a lot of the related rate problems that we will do. I do want to point out that you can do in terms of volume, you can do in terms of radius, you can do in terms of a lot of other types of things. All right, so the basic idea, just as a reminding of problem-solving process, is you want to make a drawing if it's helpful. Some problems making a drawing will not be all that helpful. Two is you want to write all the variables that you know in the problem. So you want to identify, is there time? Is there an x variable? Is there a y variable? Is it volume? Is it radius? You want to write all those out. You want to write all the information that's provided, okay, including any numerical values, what the values of x's are and y's are if they're there, any equations. So, and this is where the one thing that becomes up in related rate problems is to remind students about the fact that if you have to look up an equation, do that. But if the problem helps you build the equation, then build the equation. But don't be hesitant to look up an equation when you need it. The next step you want to do is identify what they're asking you to find. Okay, make sure you know what they find, what they're asking you to find. And then the last part is what I call is understand the context. Okay. For us, I also want to add in a very key point when it comes to working with this, is that since it's related rate problems, okay, we will actually have some sort of rate, right? We will have something per something, right? Maybe those words are too much there to write out, but that we'll have some rate. It could be miles per hour, right? And when you look at those, you want to identify that very carefully in the word problem, because that's very key. Because if you do that, then it makes you know, hey, I got a related rate. It also, in terms of the context piece, it also tells you that you are doing calculus. All right, so problem number one. If I look at problem number one, air is being pumped in a spherical balloon at a rate of, there's the word rate, and it's something per something. Okay, I have to dissect what that means. Determine the rate at which the radius, we want to look at the rate of the radius of the balloon is increasing when the diameter of the balloon is 20 centimeters. So I've got a diameter and I've got 20 centimeters. Okay, so when you do problems like this, the one thing you have to sort of catch is that there may be a formula that you have to look up. Okay, since we're talking about a spherical balloon, really in this case, I'm going to be thinking about this right away. I'm going to be thinking about the volume of it. And you have to look that up, but it's going to be 4/3 pi r cubed. Okay. All right, so that's something you'd have to look up if you don't catch it right. A spherical balloon, that's a sphere. Okay. All right, so let's go back and look at some of these things here. So it's saying that the volume, the spherical, air is pumped into the balloon at a rate of, and see it's got a cube here. So it says the volume, right? So that's a volume. So we're looking at the change in the volume over per minute over time is going to be this 5 centimeters cubed per minute, okay? If we come here and we look at, they want to find the rate of the radius change. Well, they want to find the rate of the radius change. So that's a rate. So that will be a dr dt. That's what they want to find, okay? And then they say the diameter of the balloon is 20 centimeters. Now, I could write it diameter as 20 centimeters, but actually, since I have radius here, I actually want to write this as radius. If the diameter is 20 centimeters, then the radius is 10 centimeters, okay? Okay, so it's nice to know the diameter is 20, but I actually want the radius in this problem, so I'm going to write the radius of 10 centimeters in here instead, okay? All right, so now I have all I need. I need to find dr dt, okay? So here's where that implicit differentiation comes in, because now I can go back to my formula, and I can take the d of both sides, okay? Here it's just volume, right? And so it'd be 1 times dv. I'm just going to write dv. Now watch out here. This is one mistake that sometimes students have, and I want to point out pi here is a number. It's not a variable, okay? So this is not a product rule here because you have two variables. This is pi is just a constant. So 4/3 pi is just a constant total, okay? So if that's the case, then what I want to do is when I do this, it'll just go, okay, 4/3 pi, I'll just do that. I'm going to take that 3, that's a power rule, and bring that out in front. And then the 3 will go down 1. And since we're dealing with r, there's the hidden chain rule, dr. Right, we'll just do a little cleanup there. So this turns out to be 4 pi r squared dr. Okay, and then from there, since that's step 1, taking the d. Then step 2, what we want to do is we want to divide by dt. Now, notice that the rate over here was in time. So that's what we're caring about because it's with respect to time. Okay? All right, I ran out a little space here, so hold on a second. So I'm going to take, and I'll take that dv dt, I'll divide by that side, by time. And again, just like before, I prefer to do that dt here, okay? Now, at this stage, I do have some information from before, and I could plug them in, or what I could do is I could do step 3, and since it wants dr dt, I'm going to go and solve for dr dt first. I'll do that. Well, that's pretty easy. So dr dt will just be 1 over 4 pi r squared times the dv dt. Okay? Now at this stage, I just now can plug in my information. Okay? And I'm going to flip the sides because I like the dr dt to be here. It said before that r was 10, so it's 10 squared. And we said the dv dt was 5 centimeters cubed per minute, so it's times 5. And from there, you can go through and figure out that final number. I'm not going to worry about that. Okay, but there you go. You got what you need. All right, so a second problem for us. So here we have a ladder. It's a very famous problem that's been done, and it's leaning against a building. So sometimes this is actually an example where it's nice to actually have a picture. So here's my building. Okay, here's my ladder. It's leaning against the ladder. Okay, it says it's a 10-meter ladder, so this means that the ladder is 10 meters. And and the base of the ladder is sliding away. So what's happening is the ladder is going to slide away. And the part of this problem is as the ladder slides this direction, okay, it's going to slide against the wall. It's going to slide right down against the wall. It will stay in contact with the wall the whole time. Okay, so it's sliding away at a rate. Ooh, there's a rate. Okay, and we'll come back to that. But it's sliding this way at a rate. How fast is the top of the ladder sliding down the wall? Okay, so it actually saying, and I'm going to put some labels here. It's convenient to call this the x direction, and then the wall itself, where it's convenient to call that the y direction. Okay, if it's sliding at a rate of 3 meters per second, that means in the x direction, and it's per second, so it's dt, it's going at 3 meters per second. There's that rate of change. Once you hear that, see that word rate, once you see something per something, that's very useful for you. Okay, it says, how fast is the top of the ladder sliding down the wall? If it's sliding down the wall, and again, the wall is the y direction, it wants this dy dt. That's what it wants. How fast is that doing that? When the base of the ladder is 6 meters from the wall. So it says this direction right here, the base of the ladder is 6 meters. So it's saying that x equals 6 meters. Now, it's also important to recognize that we have the Pythagorean theorem going on here. So that 10 is my hypotenuse. So I'll call it h. Okay? So for us, once you realize the Pythagorean theorem's going on here, right, is that you're going to have x squared plus y squared equals h squared. Okay? Since the ladder actually doesn't change its height, it's always 10, this is actually technically x squared plus y squared equals 100. There's my formula. Okay? So I have my formula because I'm using the Pythagorean. I have all my variables listed out, my x, my y direction. I've got I got a rate. I know what x is. I know what h is. I'm in great shape. Okay, now I can go ahead and apply implicit differentiation. I'll do that on the next page here. So I'll take the d. That's my first step. So I'll take the d of this guy. I'll take the d of this guy, 100 on the other side. Well, here you've seen this before. This will be 2x, hidden chain rule, dx, 2y, hidden chain rule, dy, constant will be 0. Then we want to divide by dt, since with respect to time. So we'll take everything here and divide by dt. This comes out to 2x dx dt plus 2y dy dt equals 0. Okay? Now here, again, I could plug things in here, but I actually want to solve for what I'm looking for. I have to remind myself that before what they told me is they want me to find this. How fast is this? How fast is this sliding down the wall? This is the piece. So in this case, what I can do now is I can go ahead and solve for dy dt. All right, well, that's pretty simple. So we have 2y dy dt equals minus 2x dx dt. Notice that I have that rate is still sitting there. Earlier when we did implicit differentiation, we divided by dx, so that dx canceled out. Because we're dividing by dt, that still has a rate there. Then I'm going to go ahead and keep going, and we get dy dt. I'm going to skip a few steps here, minus x over y dy dt. Okay? Now, I do have one small problem here. Okay? Don't know what y is. Okay? I have x. I don't know what y is, but I can actually solve for that, and I need to do some side work on it, right? Okay, I know x, we said was 6 meters. I don't know y, but we know at the time that x is 6 meters, we know that the actual length of the ladder is 10. So y will be 100 minus 36. So y, that's y squared, so y will be the square root of 64, which will be 8. Okay, so I just needed to remind myself I needed to do that. I didn't do that, but at the time that x is 6 meters when it's in the x direction, how far it's already down the wall, it will be sitting at 8 meters. That's how high it is, where the top of the ladder is hitting the wall. Okay, so from there now I can go ahead and plug it in. I've got x I said was 6. I said y was 8. And then got to make sure my x's look good here. And my dx dt, we had that rate, and I totally forgotten it now, which is just 3 meters. So if you work that out, you get negative 9 fourths, and that should be the final answer. And I could put a unit on that. All right, so hopefully that works out well, and it comes across pretty clear.